Okay, this one's pretty straightforward. Mobile, balance, torque, animation 1, animation 2, so the thing you replace it with has to be equivalent to the thing that you took out. And same way when you remove the orange block, the green and purple blocks collectively have to be balanced and have to be equal to the one you replaced. So I think you can do this, but let's take a look in case you're having problems. So all the torque problems start with this equation, but since there are positive and negative torques, you can always do it as the sum of all positive torques must equal the sum of all negative torques. Right, because the sum of the torques has to be 0. And so in this case, what you're doing, what we always do is we're going to take the bar and draw the free body diagram. So we have a bar, and there's going to be the support, force, and the mass times g, the weight of the blue block this way, and the weight of the dark green block this way. And the blue block is negative, and so every torque is an R, an F, and a sine of theta, but all these are going to have 90 degrees as the sine of theta, so we can drop that. And so we simply have R blue plus R plus F blue has to equal R green plus F green. And of course, R green, and F green is M green G, so RG equals R blue, M blue times G, so the sine of theta goes away, so we can actually take G out. And so we can, by doing the symbolic algebra, you can really simplify this down to, I didn't even look which one we're looking at. So the mass, it's the mass of the blue block that's given, and that's 0.050 kilograms, which is 50 grams. Since I don't like those decimals, I'm going to use grams. And it is important to notice that they say that the mass of the rod is negligible, because otherwise we'd have to consider that. So that's important to note. And so the solution to this is just that the mass of the green block equals R blue over R green times the 50 grams. And if you look at the figure, what are you going to guess? You're going to guess that the green block is not as massive as the blue block because it balances it being further away from the axis of rotation. So the lab part of this is you have to measure those distances. So you want to measure those distances carefully using your cursor. And you'll notice in the instructions that it says to measure these lengths to 1 digit, because you'll see this is 0.1 meters, 10 centimeters. But there's a little bit of uncertainty there. So if you round it to 1 digit, we're all going to get 10 centimeters or 0.1 meters. This is twice as far. Since it's twice as far, you can guess logically that the mass has to be half as much. And when we do this ratio of 1.1 to 0.2, we'll get 0.5. And so the green mass is half the mass of the blue mass, or 25 grams. So now you just have to repeat the same thing. The only thing is, remember, this was 25 grams that was here. So this has to be 25 grams, and it has to balance at this point. So what may not be obvious is that the sum of these two masses has to be 25 grams. And you can see that this is going to be a bigger mass than this, by whatever the ratio of those lengths are. So if this is twice as far away, that means this mass has to be twice as big as this mass, because the torques by that equation that I erased will still be balanced, but the total has to be 25 grams. And similarly, of the 25 grams here that's split between this and the orange, now once you know what the orange is, I don't want to give all the answers away, this plus this has to be equal to the orange, and whatever this is and this is, it has to be balanced around this point. So you got to measure these lengths again, and clearly out of whatever that total mass is, more of it is going to be here than here, because this has to be less massive because it's further away. And if this is again a 1 to 2 ratio, then whatever this mass is, this has to be twice as much. But the total has to equal whatever the mass of the orange one was. Okay, there were two ways of solving this next one by the concept of center of mass, and the other by sum of the torques. So the two red masses are fixed, and the blue mass is fixed, and the purple mass can be moved. And you want to move this mass, find the position to move this mass such that the center of mass, or the center of gravity, same thing in this case, is this point, which is the same thing as saying move the purple one so that the sum of the torques about this point will be 0. It reduces to the same thing, and so you can approach it either way. And so using either the torque equation or the sum of the mass equation, try to solve for the position of the purple mass. Okay, here's the algebra that leads to the answer. So you might pause the video and just look at this screen. This is using the center of mass formula. This is using the sum of the torques formula. So just pause the video and see if you can follow that, and come back and I'll explain. Okay, so XCM is 0, because that's where we want the center of mass at 0. And so I can multiply both sides by m, and that gets rid of this. And so then I'll have all this equal to 0. And so if I bring this over this side, no, if I leave this here and bring all of this over the other side, and then divide by MP, I get that XP, isolating it by algebra, is equal to this. And since M red is 1M, and M red is M, and M blue is M divided by 2, and M purple is 2 mass units, I can write it that way, and then I can cancel the M's. And remember that these numbers are negative, so the negative becomes a negative. These become positive numbers, and this will be subtracted and divided by 2, and that'll give you the answer. When we do sum of the torques, we get that the torque of the red one is a positive torque, but X red is negative, so I have to put a negative sign there. This is a positive torque, right? The distance, X2 times the force. The sine of theta is 90 because the force is acting down, so you don't see the sine of theta in here because it's 1. So there's the X, there's the force, 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 and it's all equal to 0. So I can divide through by G, and I get this. And when I write M red is just 1 mass unit, M red is 1 mass unit, M blue is mass over 2, and M purple is 2M, becomes this. So if I bring this over this side, I get the same equation as above. The position of the purple is negative the position of the red, negative the position of the red, negative position. But remember, the position of the first red is a -8, so it becomes positive. The position of the second red is 4, it becomes positive. The position of the blue is a +4, so that stays negative. And then you divide by 2, so you have 8 plus 4 is 12, minus 2 is 10, divided by 2, you get the answer of 5. Okay, I'm going to skip over number 3 for now and move on to number 4, and I encourage you, this is kind of a fun exercise where you can move the bricks around and make different arrangements and find out what's stable and what tips and so on, and then answer the questions. I think it's pretty straightforward. I don't think you'll have any trouble doing number 4. Okay, number 5. So ask yourself, look at this, is the orange rectangular box going to tip over or not? And how are you judging that? And if we make the angle steeper and steeper, obviously at some point it's going to tip, and at what point will it tip? So try and answer that question. Think about, and obviously the answer involves torque. So think if you can answer that question before you listen to my explanation. Okay, the answer is it's not going to tip over, and the way you would figure that out is you would go to the center of the box where the force of gravity is going to be the tipping force, right? It's gravity that's going to tip it over. So you find the center, that's not really the center, and then you draw a line straight down, and you can see that the gravity force is still within the base. And so what happens? Eventually the thing's going to tip, and when it tips, what's the axis going to be? The axis is going to be right here at the corner. So when the angle is such that the gravity force points to the corner, it will be as far as it can go before it tips. If you go any further, it will tip. So that's the physics torque part of this problem. Let's now go and answer the questions that are asked. Once again, I think it's useful that you try and answer these questions on your own without waiting for my explanation. And maybe you'll find a way of doing it that's better than my way of doing it. So I'm just going to show you how I did it. There may be other ways. So the first question is, what is the angle of the green incline? So you put your cursor here and get the xy coordinates here, the xy coordinates here, and the x coordinate will be the same, and the difference in the y coordinates is the height of the box. And then you get the point here and the point at the tip, and that will give you the length of the box, and then you can use the y over the x, which will be the inverse tangent of the angle you want. Now you need the height and width of the box, but since it's not flat, you can't just measure it because the cursor measures the x and y coordinates. So what you have to do is measure, get the coordinates here, the coordinates here, and then you can use those to find the length of the box. And the way I would do it is the x coordinate will be that. I mean, the difference between the x coordinates and the difference between the y coordinates will be that. And so this is your delta x, this is your delta y, and those are two sides of a right triangle where the length of the box is the hypotenuse. And you can see that the length of the box is pretty close to the height that you get from the y component, but not exactly right. And it's going to be hard to draw this, but down here you would get the components at this point and at this point, And again, you would have a triangle like that, where this is your delta x, this is your delta y, and the width of the box would be the hypotenuse. So you want to make those measurements carefully and get that information. Now, what is the maximum angle before the yellow box will tip over? And so that means you have to find the angle at which the center is directly over the corner. Okay, so think about how you're going to do that. So compare what you did to what I did. If you have a better way, let me know. So anyway, I drew a box like this. And remember, when the diagonal, what it means is when the diagonal, which passes through the center, is perpendicular to the ground, when it is straight up and down, that's the point at which the box is about to tip. So when you do that drawing, that means that the angle here is the angle that you're tipped at, right? You have to, so this is, if the box were like this, straight up and down, then to get this diagonal straight up and down, you have to tip it through an angle of that much. So this angle, of course, these two angles are equal, and that would be equal to the track angle. You should be able to convince yourself of that. And so that becomes very easy. You have the width of the box and you have the height of the box, and so the angle at which it's going to tip is this angle, which is the inverse tan of the width over the height, which you already have those numbers. And that should be a bigger number than you got for the green ramp angle. Okay, number 6. This is a very fun animation, I think. So read the description carefully. What you're doing is you're looking at a table, and there's a rod on the table, and we're looking at it from above down. So the table's pushing up on the rod with a normal force coming out of the screen, and the weight of the rod at its center of mass is acting down into the screen through the table. And when you press animation 2, you see several horizontal forces acting on the rod. And so what you have to do is you have to apply a single force that will make the thing in equilibrium. And so you're satisfying 3 conditions. What are those 3 conditions? What are the 3 conditions? You're waiting for me to answer? No, write down the 3 conditions. Okay, you wrote them down? I don't see that you wrote them down. Try again. What are the 3 conditions? So there they are. There are 3 equilibrium conditions. The sum of the torques have to be 0. The sum of the forces in the x direction have to be 0, and the sum of the forces in the y direction. So the single force that you're going to apply has to satisfy those 3 conditions. And when you go to animation 3, it gives you that blue arrow, which is the force, which you can drag around, which you can make in any direction at any length. So what do you have to find out? You have to find out what x and y coordinates this arrow needs to make the sum of the forces x and y 0, and then you have to place it in the right position such that the sum of the torques is 0. And if you do that correctly, when you check your answer, you'll see, oops, no. You see there's a net torque of 0.046, and there's an unbalanced, I didn't cancel out the forces because there's a net force along negative x and a net force along positive y. So in order to get rid of that, I have to stretch this arrow. Let me see if I can still do that. I have to stretch this arrow well, it's not working. Let me pause. So you see I can stretch the arrow. So I need more X component, and I need more negative Y component. So if I make this bigger, when I check my answer, that red arrow should be less. Oh, it's not checking. But anyway, oh, there it is. Oh, so I compensated too much. But you see the net torque has gotten bigger, so that means that the position of this thing needs to be changed to compensate for the net torque. So anyway, play it like a game. Before you do the physics and calculate all the torques, see if you can find the single blue arrow, the right length, the right position, the right X and Y components, and the right position for the right torque to get everything to be zero. And then you can proceed with the calculation. Now, when you look at this diagram, right, you can see that there's no X force. This has an X force in the negative direction. This has an X force in the negative direction, and this is a negative X force. And that's why you see the blue arrow has to have so much positive X to it. You should try this before I tell you too much. See if you can find it on your own. And it's not obvious, the Y part. So this has a Y part. This is a big Y part. This is negative. This is negative. So apparently there is some net positive Y force because you see we have some negative force in this. And then think about whether the net torque is positive or negative. Here we're getting a positive torque, so the position here is going to cause this to be positive. So what you would expect is, I don't know if I can do this, but if I slide this, well, I can't do it, but if I slide the arrow this way, which I'm not able to do, the torque should become less. Okay. So the basic idea, remember when we added vectors, we used to use this table method and we had X and Y components. So basically what you're going to do for each of these forces, each of the 5 forces, is you're going to find the X and Y components, and some of those components will be 0. And then you're going to add them together, and whatever you get for the sum, your blue vector has to have components which are equal and opposite, right? Why? Remember, because we want the sum of the X components to be 0 and the sum of the Y components to be 0. So our blue vector will have components which are the opposite of these components, and then they'll sum to 0. I don't mean that to be a 0, just whatever that number is. Then once you have that, then you have to calculate all the torques due to those 5 items, and you can calculate it, and once you calculate it, you have to position that blue vector, right? Because you can't, once these components are fixed, you have to keep that blue vector the same X and Y component, but you can adjust the torque by adjusting the position at which you place the blue vector along the rod. And that way you'll adjust the torque to be 0. And so by calculation method, you should figure out exactly what the X and Y component should be and what the position of that vector should be. All right, the only one I didn't talk about was number 3, but I think it's pretty straightforward. You'll find your way into the website and you'll use, by flipping that switch, you'll go to the balance beam and you can put on a ruler, and then you can pile bricks on here according to the instructions. and you can solve for torques. Pretty straightforward torque problem. And there's two people on the seesaw, another torque problem. So I don't think you'll have any trouble with this. If you do, send me an email. Okay, that's it for this lab.